Hello children, once again welcome back to Physics with Sanoop. See, now we are going to discuss the magnetic effects of electric currents. See, before that you have to take a notebook and pen and while watching this video you have to note down all the important formulae, equations and everything that you feel it is important and it is to be noted down. Okay, and see why after this video you have to practice yourself and see if you take any problem, see the tool necessary to solve that problem will be there in this video. So you have to solve the problems by keeping that notebook open. Take any problem, the tool required will be there in the notebook. Okay, you have to just take the tool and apply it. Okay, now first the thing is Bide-Savart's law. Okay, that gives the magnetic field intensity due to a current element. Here there is a current carrying conductor and the current in it is capital I. So I have taken a small element. Suppose dl is the length of the elements. See, dl is the length of the elements. Now current element is considered as a vector and its magnitude is equal to the product of the length of the element and current through it, and its direction is along the conventional direction of electric currents. Okay, now this is the current element and this is the point where we have to find the intensity of magnetic field due to this current elements. So first you have to draw a position vector from the center of the elements to the point of observation. So this is the center of the element and this is the point of observation. So this is the position vector. Okay, and theta is the angle between current element and the position vector. Okay, and the magnetic field intensity is given by dB equal to mu 0 by 4 pi I dl cross r cap. It is a unit vector along the direction of this position vector, say r, along the direction of this position vector r. Okay, so and this mu 0 is the permeability of vacuum, and here we assume that the current element is in vacuum. Okay, so we will see its magnitude dB will be mu 0 by 4 pi I dl sin theta by r square. Okay, where r is the distance between the current element and the point of observation. See, the most important thing that you have to understand, if you take any points along the length of the elements, means see, if this is the point of observation, the angle is theta. See, if here is the point of observation, the angle theta got reduced. Okay, now if here is the point of observation, the theta is again reduced. Okay, now see, now suppose the point of observation is here, then theta is very small, and if the point of observation is here, then theta will be 0. Then sin theta equal to 0 and magnetic field will be 0. So a current element will not produce any magnetic fields at any point along its length. That is the most important thing that you have to understand. Okay, a current element will not produce any magnetic field at any point along its length. Okay, now see what we have next. Okay, now this is a straight conductor carrying a current capital I. Okay, and here is the point of observation at a perpendicular distance a, small a, from the conductor. Okay, now we have to draw two lines from the point of observation to the two ends of the conductor, and these two lines make an angle theta 1 and theta 2 with the perpendicular drawn from the point to the conductor. Okay, now the magnetic field intensity is given by mu 0 I divided by 4 pi a sin theta 1 plus sin theta 2. If the conductor is infinitely long and the point of observation is somewhere near its middle, means see, along this direction it goes to infinity and along this direction also it goes to infinity. Okay, so the graph, see, the diagram will be like this. Okay, see, this is that line. This broken line will touch the conductor only at infinity. Okay, so this angle theta 2 will be 0 and theta 1 also equal to 0. Okay, so the magnetic field will be B equal to mu 0 I divided by 2 pi A. Okay, then how do we get the direction of the magnetic field? That is given by the right hand rule. You have to hold the conductor in the right hand with the thumb along the direction of electric currents. Then the fingers curl along the direction of magnetic fields or magnetic lines of force. Now if the conductor, see here the conductor carries a current like this. Okay, the thumb must be pointing along the direction of electric current. Now if the current is reversed, means if the current goes down, then you have to hold the conductor like this, and the magnetic field will be in concentric circles surrounding the conductor. Okay, and now let us consider a semi-infinite conductor. Means the point of observation is at one end of the conductor, and the conductor goes to infinity, see on the other sides. Okay, this goes to infinity. Okay, so theta 1 will be equal to 90 degree, because this line will meet the conductor only at infinity, but theta 2 will be equal to 0. Okay, so we will get the expression for the magnetic field intensity as mu 0 I divided by 4 pi a, semi-infinite. Okay, and it is equal to half of the magnetic field near the center of an infinitely long straight conductor. Okay, now let us see what we have. See, you have to note down all these formulae in a notebook, and while solving the problems you have to keep that notebook open. Please do not try to memorize any formula or any equation. Okay, now see, we have to find the magnetic field intensity along the axis of a circular loop of radius small a carrying a current capital I. Okay, and this is the intensity of magnetic field along the axis. It is mu 0 I a square divided by 2a square plus x square whole raised to 3 by 2. Okay, now if there are n loops, this is the field due to one loop. If there are n loops, we will have to multiply with capital L. So this is the expression for the magnetic field intensity on the axis due to n loops. Mu 0 n I a square divided by 2a square plus x square whole raised to 3 by 2. Okay, now suppose we want to find the magnetic field intensity at the center. Means the point of observation will be, see, before that the magnetic field at this point will be along the axis, see, like this. Now here is the point of observation. See, it is represented by capital P. This is the point of observation, and suppose we want to find the magnetic field intensity due to the current loop at its center. Then see, we have to reduce this one. Okay, we have to reduce this one, so x go on decreasing, and at the center the value of x will be 0. Okay, at the center the value of x will be 0. Okay, now see, at center x equal to 0, so BC, magnetic field intensity at the center, that is equal to mu 0 Ni divided by 2a. Okay, now let us consider 2 points, one at the center and one on the axis of the loop. See, at the center x equal to 0, and on the axis of the loop, or anywhere on the axis, anywhere else on the axis of the loop, x will have a different value. Okay, so if we compare the magnetic fields at the center and at a point on the axis, see, the difference will be only in this factor. See, only in this factor. Okay, the rest of the expression will be same for both the points, for the center and at another point on the axis. So let us say the magnetic field intensity is proportional to 1 by a square plus x square whole raised to 3 by 2, or let us say it is inversely proportional to that factor. So magnetic field intensity at the center divided by axis, as it is inversely proportional, see, on the right side it will come axis by center, on the left side center by axis. As it is inversely proportional to that factor, on the right side it must be axis by center. On the axis x is non-zero, and at the center it is equal to 0, so it will be a square plus x square whole raised to 3 by 2. Okay, now here we have to find the intensity of magnetic field at the point capital O. Here there is a straight conductor, then a circular arc, and then again a straight conductor. See, as this point of observation capital O is along the length of this conductor, this straight conductor will not produce any magnetic field at the point of observation. Okay, now see, this point of observation is along the length of this straight conductor also, so this straight conductor also will not produce any magnetic field at this point O. Okay, now the magnetic field at the point O will be only due to the circular arc. See, due to a complete circle, the magnetic field at the point O will be mu 0 I divided by 2a. Okay, and this arc subtends an angle theta. So the field at these points, see, for full circle means if the angle is 2 pi, for full circle means the angle subtended at the center is 2 pi radian. If the angle is 2 pi, say magnetic field is B. Okay, and for unit angle it will be B by 2 pi for unit angle. Okay, and for an angle theta it will be B by 2 pi into theta. Means the magnetic field due to the whole circle into theta by 2 pi. Okay, so this is the magnetic field at the point of observation. Okay, that is mu 0 I divided by 2a into theta by 2 pi, mu 0 I divided by 2a into theta by 2 pi, that is the magnetic field at the point of observation. Now children, we have a circular loop of radius small r, okay, made from a uniform resistance wire. Okay, see, this is the circular loop, this is the circular loop. It is made from a uniform resistance wire, and the resistance per unit length, that is lambda. Okay, now I have connected a cell of voltage capital V across two arbitrary points. Okay, two arbitrary points, one is this one and the other is this one. Okay, and see, then these 2 points divide the circular loop into 2 arcs. Okay, one arc subtends an angle theta and the other subtends an angle 2 pi minus theta. Okay, now suppose some current is drawn from the cell. Okay, some current is drawn from the cell. Okay, that current reaches this point where it gets divided into 2. Okay, one part of the current passes through the upper arc and rest of the current passes through the lower arc. Okay, now how do we find the magnetic field at the center of a circular loop? We have to use the right hand rule again. Now curl the fingers along the direction of electric current, then the thumb will point along the direction of magnetic field. Okay, now here see, the current in the upper loop is along in the clockwise direction. Okay, so we have to curl the fingers like this. So magnetic field at the center of the loop due to the current in the upper arc will be along the inward normal. See, this is the way we have to curl. So the magnetic field at the center due to the upper arc will be along the inward normal. Now let's consider the current through the lower arc. Okay, and through the lower arc the current is in the counterclockwise direction. So we have to curl the fingers like this. So the thumb will be pointing along the outward normal. So the magnetic field at the center of the loop due to the current in the lower arc will be along the outward normal. Or in short, the magnetic field at the center of the circular loop due to the 2 arcs are in opposite direction. Okay, so the resultant field will be the difference of these 2 fields. Field due to the upper arc minus field due to the lower arc. Okay, now let us find the magnetic field at the center due to the upper arc, in which current is I1 and the field, let us represent it by B1. Okay, so B1 mu 0 I1 divided by 2R into theta by 2 pi. Okay, now see, multiply both the numerator and denominator by R lambda, where R is the radius and lambda is the resistance per unit length. Okay, so when you multiply the numerator with the R and lambda, see, mu 0 I1 already there, theta also there. Okay, so R and lambda will come in the numerator. In the denominator already there is an R. When one more R comes, it will become R square, and here we will get 2 pi lambda, right? Okay, now what is the length of this arc? It is angle into radius, or R theta. R theta is the length of the arc, and lambda is the resistance per unit length. So for unit length, resistance is lambda. So for a length of R theta, resistance will be R theta lambda. Okay, so this R theta lambda is the resistance of the upper arc through which the current is I1. Okay, so let us write this R theta lambda, that is the resistance of the upper arc. Let it be represented as capital R1, resistance of the upper arc. So in the numerator we will get I1 R1. That is the voltage across the upper arc. Okay, see, now when the cell is connected across these 2 points, there are 2 arcs connected across the same 2 points in parallel, okay, across the cell. So the voltage across this arc will be the applied voltage. Voltage across this arc also will be the applied voltage, because both are connected in parallel across the same source of voltage, right? Okay, now we can replace this I1 R1, that is the voltage across the upper arc, that is equal to the applied voltage or voltage of the source. Okay, so magnetic field at the center of the loop due to the upper arc, that is mu 0 by 4 pi V by lambda R square, V by lambda R square. Okay, now let us find the magnetic field at the center due to the lower arc. See, what is the difference between the upper arc and lower arc? There is difference in the angle subtended. But see, the magnetic field at the center, in the expression there is no angle subtended at the center, or let us say the magnetic field is independent of the angle subtended at the center in this particular case. Okay, then the current through the 2 arcs are different, but current also does not appear in the expression. Okay, since this mu 0 by 4 pi, that is same for both the upper and lower arcs. Voltage, that is same for upper and lower arcs. Lambda, resistance per unit length, same for both the arcs. Radius, it is also same. So if this is the magnetic field at the center due to the upper arc, the same will be due to the lower arc at the center, but these two will be in opposite direction. So the resultant field at the center will be 0, irrespective of the angle subtended by the 2 arbitrary points at the center. Okay, so wherever you connect this cell, the resultant magnetic field intensity at the center will be 0. Now children, we have Ampere's circuit law, that is somewhat analogous to Gauss's law in electrostatics. In Gauss's law, we have to integrate the intensity of electric field over a closed surface, or it is the surface integral. But here we have to integrate the magnetic field over a closed path, or here it is the line integral. Closed integral B dot dl equal to mu 0 times the current threading through the closed path, or current penetrating through the closed path. Okay, now see, let us find the magnetic field intensity due to an infinitely long straight conductor at a perpendicular distance r from it when it is kept in vacuum. Okay, so this is the point of observation. In order to apply this Ampere's circuit law, we have to consider a closed path around the conductor. Okay, now see, this is B dot dl performed, integration performed over a closed surface, that is circle here. B into 2 pi r equal to mu 0 times I, and B will be equal to mu 0 I divided by 2 pi r. Now let me plot this magnetic field against the distance r. Then in order to find the shape of the graph, the general procedure, not only in this case, anywhere you can apply this. The general procedure is, you will have to replace the quantity that is to be plotted along the x-axis with the x, and the quantity to be plotted along the y-axis with the y. Here I am going to plot this r along the x-axis and b along the y-axis. Let me take this r to the left. Okay, so it will become RB, small rb, in which r is along the x-axis and b is along the y-axis. Okay, so I'll get xy equal to mu 0 I by 2 pi. The quantity on the right side is a constant, so the equation will become xy equal to constant, and it is the equation just like PV equal to constant, or it is the equation of a rectangular hyperbola, and this is the graph of rectangular hyperbola. Okay, now this is an infinitely long current carrying pipe, means it is hollow and it is cylindrical, and its radius here it is small a. Okay, if we take any closed path inside the pipe, no current is threading through the path and the magnetic field intensity will be 0. Okay, just like we have done in electrostatics, that is the spherical shell. Okay, inside the spherical shell, electric field intensity was 0. Okay, just like see, the magnetic field intensity inside the pipe will be 0. Okay, and outside the pipe, the magnetic field varies exactly similar to the field due to an infinitely long straight conductor. Okay, and this is the function of the magnetic field. Okay, and it is given in two steps. Okay, B, magnetic field intensity is 0 when small r, distance of the point of observation from the axis. Less than A means inside the pipe, and greater than or equal to means on the surface or outside. Okay, so here also if we plot the graph, see the magnetic field is 0 from the axis up to the surface, from the axis up to the surface, and on the surface the magnetic field intensity is mu 0 I by 2 pi a, and beyond the surface, okay, and it varies as a rectangular hyperbola. And now next, infinitely long current carrying solid cylindrical conductor. Okay, and the conductor is of radius small a, it carries a steady current capital I, current is distributed uniformly over the cross section. Okay, current is distributed uniformly over the cross section. Okay, now when small r is less than a means inside the conductor. Okay, so B dot dl, that will be B into 2 pi r, and mu 0, then I by pi a square is the current density, current through unit area. Okay, this is the current through unit area, and the area enclosed by circle of radius small r inside the conductor will be pi r square. Okay, so this is the magnetic field, and if we plot, see this expression will be valid only when small r is less than a or inside the conductor. Okay, now if we plot this, this capital B is to be plotted along the y-axis, so let us replace it by y. Okay, and see this one, this much is constant. Okay, and small r is the quantity to be plotted along the x-axis, so let me represent it by x. If this if this encircled quantity is represented by a constant, say m, then we will get y equal to mx plus nothing, mx plus 0. That is the equation of a straight line passing through the origin. So the magnetic field, if we plot against the distance from the axis, we will get a straight line passing through the origin inside the conductor, and outside it will be exactly similar to the field due to a pipe or infinitely long straight conductor. Okay, so from the axis up to the surface, okay, it is a straight line, and beyond that it is a rectangular hyperbola, and this is the function which represents the magnetic field due to a solid cylindrical conductor in which the current is distributed uniformly over its cross section. Now children, let us find the magnetic field due to a toroid or inside a toroid. Toroid means a solenoid in circular shape. Okay, now see, in order to apply this Ampere's circuit law, we have to consider a closed path inside the toroid like this. Okay, if the average radius of the toroid is 2 pi r, so B dot dl will be B into 2 pi r, average radius. Why do we call it average radius? Because this is the inner radius and this is the outer radius. Okay, so average radius we have to take. Now B dot 2 pi r. See, if this is the closed path, then how many wires will be threading through it? See, as one turn goes like this, it carries a current I. Okay, and when another turn goes, again current I. There are small n turns per unit length, and the total length will be 2 pi r. So the total number of turns will be 2 pi r into small n, and each turn carries a current I. So the total current threading through this closed path will be n into 2 pi r into capital I. Okay, 2 pi r on both sides, that can be cancelled, and ultimately we will get B equal to mu 0 Ni, that is the magnetic field inside a toroid. Inside a toroid means here, inside the toroid. Okay, and not in this space. Okay, inside toroid means here. Okay, in this space, the magnetic field is mu 0 Ni. Now suppose we have a single turn of radius capital R carrying a current capital I like this. Okay, it carries a current capital I. Now this wire is wound more sharply so that radius is reduced and the number of turns is increased. Now it is wound into n turns of smaller radius like this, n turns. But the total length of the wire will remain constant. Originally it is 2 pi capital R. And now see, each turn is of length 2 pi small r and such n turns are there. So total length will be n into 2 pi r. 2 pi on both sides can be cancelled. So capital R will be n into small r. This is the magnetic field at the center of the original single turn coil. And see, B dash, magnetic field of this small or coil with a smaller radius and more number of turns. Okay, that will be mu 0 Ni divided by, see, mu 0 Ni divided by 2R. Mu 0 Ni by 2R. That is B dash. That we have to find out. Okay, let me multiply both the numerator and denominator by n. So in the denominator we will get 2 small r small n. And small r small n we can replace by capital R. Okay, in the numerator there is n and one more n, so it will become n square, and n square mu 0 I divided by 2r, that is equal to b. Okay, so we will get b dash equal to n square b. So when a coil, single turn coil, is wound more sharply so that there are small n turns of smaller radius, then the magnetic field will become n square times. Now current loop as a magnetic dipole. Okay, now see, this is the expression for the intensity of magnetic field along the axis of a current loop at a distance x from its center. Okay, mu 0 Ni a square divided by 2x square plus a square whole raised to 3 by 2, where a is the radius of the loop. See, here is the loop, and here I have shown only one turn. If there are capital N turns, the magnetic field at this point will be mu 0 Ni a square divided by 2x square plus a square whole raised to 3 by 2. Now suppose this point of observation is at a large distance from its center. Okay, then this a will be very small compared to x, and a square will be again much smaller than x square. So x square plus a square will be approximately equal to x square, and then this equation will become mu 0 Ni a square divided by 2x cube, because a square can be neglected, 2x cube. Okay, but in the denominator I have written mu 0 by 4 pi. See, in the denominator actually there is only 2, only the factor 2, but I have written 4 pi. Means I have multiplied the denominator by 2 pi. So I have to multiply the numerator also by 2 pi. Okay, in the numerator there is no 2, there is no pi. Okay, so I have put 2 here and pi here. Okay, mu 0 Ni a square, that's fine. This pi a square, that is the area of the loop. So that pi a square is replaced by capital A, that is the area of the loop. Then n is there, I current through the loop, and this is the area, then 2 and mu 0 by 4 pi x cube. Okay, where capital A is the area pi a square. Okay, now what is the magnetic field along the axis of a magnetic dipole? Magnetic dipole, see, field along the axis of a magnetic dipole means, suppose we have a magnetic dipole like this, here south pole and here north pole. Okay, it is a short magnet or short magnetic dipole, and this is the center of the magnet, and here is the point of observation which is at a distance x from the center of the dipole. Okay, then the magnetic field at this axial position will be mu 0 by 4 pi into 2m by x cube. That is the magnetic field along the axis of a magnetic dipole. Now let us see the expression for the magnetic field along the axis of a current loop. Okay, here we have mu 0 by 4 pi, here also we have mu 0 by 4 pi. In the denominator there is x cube, here also we have x cube. Okay, here we have 2, here also we have 2. Okay, then here we have m, and in this expression what stands for m? That is NIE. That is NIE. So the field along the axis of a circular current loop varies exactly similar to the field due to a magnetic dipole along its axis. Okay, and see, we can say a current loop acts as a magnetic dipole of moments equal to NIA, of moments equal to NIA. If the current loop acts as a magnetic dipole, there must be a south pole and a north pole. So one side of the loop, see, if I hold a paper paper, thin paper. Here there will be two sides for that paper, this side and back side. Okay, so if I hold a loop like this, there will be one side and back side. So one side will act as north pole and the other as south pole. How do we identify which is north and which is south? Here is the way. Suppose the current is in the counterclockwise direction, you have to curl the fingers of your right hand like this. Then see, thumb points outwards. Thumb points along the direction of magnetic field. Thumb points along the direction of magnetic lines of force which originate or come out of north pole rather than originate. Magnetic lines of force come out of north pole. See here, if you curl the fingers along the direction of electric current, then thumb is pointing outwards or the magnetic lines of force are outwards. Magnetic lines of force will come out of only a north pole. So this must be a north pole. And see, if the current is in the clockwise direction, okay, then the thumb is along the inward normal. So the magnetic lines of force are along the inward normal. Okay, so the magnetic lines of force are going to, magnetic lines of force will go to south pole only. So here there will be south. So what you can do now, you can simply write capital N and put arrows at the two ends. Okay, two ends of N. Then that arrows will point along the direction of electric current. Or if you write is S corresponding to south and put arrows at the two ends, that arrows will be along the direction of conventional current. Now let us find the magnetic field due to a solenoid. Okay, here the point of observation is somewhere near the center. Okay, and see, there are small n turns per unit length and it carries a current capital I. Okay, then this is the expression for the magnetic field intensity on the axis, and outside that solenoid the magnetic field intensity is negligible. Okay, so mu 0 Ni divided by cos theta 2 minus cos theta 1. Okay, now if the point of observation is somewhere near its middle and the solenoid is infinitely long, means this goes to infinity on this side and it goes to infinity on that side also. Okay, so this theta 2 will become 0 and theta 1 will become pi. See, you can see I have marked theta 2 here, this one theta 2, okay, and this one theta 1, okay. If it is infinitely long on both sides, theta 1 will be pi and theta 2 will be 0. Okay, so theta 1 equal to pi and theta 2 equal to 0. So cos 0 minus cos pi is minus 1. Cos 0 is 1 minus minus 1, that will be 2. So we will get the magnetic field inside the solenoid as mu 0 Ni. Same as the magnetic field inside a toroid. Toroid means it is a solenoid in circular shape. Okay, now if the solenoid is semi-infinite, means it goes to infinity only on one side and the point of observation is at one end of the solenoid, then it's called semi-infinite. In such a case, theta 1 will be pi and theta 2 will be pi by 2. Okay, so cos pi by 2, that is 0 minus cos pi. Cos pi by 2, 0 minus minus 1. So it will be mu 0 Ni by 2. So the magnetic field at one end of a semi-infinite solenoid will be equal to half of the magnetic field intensity at the center of an infinitely long solenoid with the same number of turns per unit length and same current. Now next thing is force on a charged particle moving through a magnetic field. Okay, now suppose the magnetic field is along the horizontal. Okay, so this is the direction of the magnetic field. A particle of charge Q is fired or projected into the magnetic field with a velocity v at an angle theta with the direction of the magnetic fields. Okay, like this. Okay, this one is magnetic field along the horizontal and this is the velocity. The angle between these two vectors is theta. Okay, then the force that is given by F equal to QV cross B, and in magnitude F equal to QVB sine theta. Okay, and see, this force will be perpendicular to velocity. Okay, so the dot product of force and velocity, that is the power, will be 0 always. See, the instantaneous displacement is along the direction of instantaneous velocity, which is always perpendicular to force. So the work done by this force at every point on the path of the particle will be 0. Means no work is done by this force. Okay, work done equal to 0. Next, motion of a charged particle through a transverse magnetic field. See, uniform transverse magnetic field is represented by crosses. If the magnetic field is represented by crosses, then the field is along the inward normal, Okay, and let us assume that the field is uniform. A particle of mass m and charge q is fired into this magnetic field. See, the initial velocity is perpendicular to the magnetic fields. Velocity is in the plane of the board and magnetic field is along the normal to the plane of the board. So the particle will execute uniform circular motion. The necessary centripetal force is provided by the magnetic force QV cross B. Here velocity and field are perpendicular, so QVB sin 90, that is equal to 1 sin 90. So it will be QVB. So MV square by capital R is the radius of the circle, that is equal to QVB, and we have the expression for the radius, that is MV by QB. MV is the linear momentum. When a particle of mass m is moving with a certain velocity, it possesses kinetic energy. So we have a relation between linear momentum and kinetic energy of a moving particle. See, linear momentum is represented by small p. If its kinetic energy is k, then the linear momentum is under root 2 into mass into kinetic energy. Okay, divided by qb, that is the radius of the circle in which the particle moves. The motion will be uniform circular motion. Okay. And what is the angular speed? It is v by r. See, from here v by r will be qb divided by m, qb by m. So angular speed, that is independent of the speed of the particle. It is independent of the radius of the circle in which it is moving. Okay, so omega equal to qb by m, and period, time required for one complete revolution, that is equal to 2 pi m by qb. See, whether it is in a smaller circle or longer circle, okay, period will be the same. Period depends only the mass of the particle, the charge and the magnetic field through which it is moving. Okay, this is the case when particle is projected into a transverse, means normal, perpendicular magnetic field. Now suppose, this is a plane. If, this is called a normal. See, this is called a normal. And this is called a tangential to the plane. And if it is like this, it's called oblique. Now let us consider the motion of a charged particle through an oblique magnetic fields. Not tangential and not normal. Okay, oblique magnetic field means, the magnetic field is along the horizontal and it is directed towards right. And this is the magnetic field and the particle is projected like this. This velocity v can be resolved into two components. See, v sin theta perpendicular to the direction of the magnetic fields and v cos theta along the direction of the magnetic fields. See, when a particle is moving through a magnetic field, the force is qv cross b, cross product of velocity and magnetic fields. Here the particle has got two components of velocity. One along the direction of magnetic fields. So if you find the cross product of this v cos theta components and the magnetic field, it will be 0. Means there is no force on the particle due to the component v cos theta. The particle will experience a force only due to the component v sin theta, that is perpendicular to the magnetic fields. So what happens? This v sin theta will turn the particle in a circle. Okay, this v sin theta will turn the particle in a circle. Now let us find the direction of the force on the particle due to the component of velocity v sin theta. Now let us consider v sin theta alone. Okay, so positively charged particle will be moving like this. Here it is upwards. So the electric current will be in the upward direction. I have to apply this Fleming's left hand rule. Okay, current is along the, or this middle finger is to be pointed along the direction of electric current. Magnetic field is towards right, so forefinger must be towards right. Let me turn. Okay, see, this is v sin theta, direction of v sin theta, that is the direction of electric current due to the motion of positive charge. This is the direction of magnetic field, so force will be along the inward. Okay, so this v sin theta will turn the particle like this. Okay, if the body has only the component v sin theta, it might have been moving, or it must have been. moving in a circle like this. Okay, so V sine theta will rotate the particle in a circle like this. Okay, with the constant speed V sine theta in a circle of radius r equal to m. Instead of V, you have to put V sine theta divided by QB. And omega, see, velocity divided by radius of the circle V sine theta by r QB by m. Okay, see, so V sine theta will turn the particle in a circle. At the same time, V cos theta will remain unaffected and it will take the particle along the direction of the magnetic fields. See, you might have seen, see, springs in ballpoint pen. So the particle will be following, or let us say moving along the circumference of that spring, and it is called a helical spring. The path followed by the particle is called a helix. Okay. Now what do you mean by the pitch of a screw gauge? Pitch of a screw gauge. See, if I turn the screw, the tip of the screw will advance in the forward direction. See, through what distance the tip of the screw will advance in one complete rotation. It is called pitch. In screw it is pitch, everywhere it is the pitch. Okay. Now see, if we turn it if we give one complete rotation, the distance through which the tip of the screw advances may not be enough to measure. So what usually we do now, we will turn it 5 times or say 10 times. Then there will be a measurable distance. It will measure, see, that distance we will measure, and that distance will be divided by the number of rotations so as to give the distance through which the tip of the screw will advance in one rotation, and it is called pitch of the screw. Similarly, when this particle follows a helical path, see, it is rotating and at the same time it moves along the direction of the magnetic fields. So through what distance the particle will advance during one complete revolution, that is called a pitch of the screw. So we have to measure the distance along the direction of the magnetic fields. Along the direction of the magnetic field, the velocity is constant. So the distance through which it travels will be simply the product of velocity and time. Okay, we have to get the displacement in one period, and that period equal to 2 pi m by qb. So the pitch will be v cos theta, velocity into time, so 2 pi m by qb into v cos theta. Now let's consider the motion of a charged particle through crossed electric and magnetic fields. Means in this case, the electric field, the magnetic field and the velocity vector are mutually perpendicular. Okay. Now see, when a particle is moving through electric field as well as magnetic field, the force will be electric force plus magnetic force. Electric force is QE and magnetic force will be QV cross B. Okay, crossed electric and magnetic fields means these two field vectors are perpendicular to each other. Okay, and the particle is moving perpendicular to both the fields. Okay, as an example, let us consider the particle projected along positive x direction and its velocity is given by vi cap. Okay, the electric field intensity is along positive y direction and it is given by ej cap, and the magnetic field intensity is positive z direction. Okay, and it is represented by bk cap. Okay, I have shown this is the positive direction of x-axis, y-axis and z-axis. Okay, see, k cross i is j. As this cross product is anti-commutative, I cross k will be minus j. Okay, now let us find v cross b. V is along positive x-axis I cap and b is along k cap. So product VB, then I cross k cross I is j. I cross k will be minus j. So V cross B will be minus j cap VB. And the force is electric plus magnetic. Okay, so force will be QE j cap minus QVB j cap. Okay, this j is common to both the terms, it can be taken outside. So the force F is equal to QE minus VB j cap. If the resultant force acting on the particle is 0, see, what are the direction along which the particle experiences force? See, magnetic force is along negative y direction, means magnetic force will be downwards and electric force will be upwards. Okay, if the particle has positive charge. If these two forces balance each other, then the particle will travel undeflected. Okay, resultant force on it is 0. If it travels undeflected, its velocity will be E by B. So irrespective of the mass of the particle, irrespective of the charge of the particle, all the particles with a certain velocity v equal to E by B will be traveling undeflected. So we can choose, see all the particles moving with a certain velocity from a collection of large number of charged particles. Okay, by using this method, all the particles with a certain velocity will be moving undeflected. Okay, and this is called velocity selector. Now children, see here we have a negative plate on the top, positive plate at the bottom. So there will be electric field between these two plates, and it is directed from positive plate to the negative plate, means upwards. So electric field intensity is along positive y-axis. Okay, and magnetic field intensity. You see here we have south pole. So the pole, pole on the other side must be north, and intensity of magnetic field is from the north pole to the south pole. Means north pole is behind this and south pole is in front of it. Okay, so the magnetic field will be along the outward normal. Okay, along the outward normal, or it is along the positive z direction. Okay, now let us find the direction of the magnetic force. See, we have a upper negative plate, lower positive plates. We have south pole here and north pole here. So the magnetic field will be from north pole to the south pole, means along this direction. Okay, this side is open and this side is also open. There are plates or poles on the top, bottom and front side and back side. So the particle can move like this. Okay, the electric force acting on a positively charged particle will be upwards along positive y direction, and magnetic field, let us find the direction by using the Fleming's left hand rule. As the positively charged particle is moving like this, that is the direction of the current. Magnetic field is outwards. See, this is magnetic field and the current will be towards right. Okay, this is magnetic field, this is current, this is my left hand. So the force on the charged particle will be directed downwards. So magnetic force along the negative y direction. Okay, if these two forces balance each other, the particle will travel undeflected. Now see, let us find the force on a current element kept in a magnetic field. See, this is a current carrying conductor, and I have taken a small element of length dl. When we take a small element, it must be straight, and here the current elements, it is considered as a vector, and its magnitude is the product of current and the length of the element, direction along the conventional direction of electric currents. Okay, so I have a current element, it's a vector, and magnetic field. The angle between these two vectors is theta. Okay, now see the current, suppose it carries a current capital I and is given by minus NaeV, where E is the electronic charge, V is the drift velocity of electrons, N is the number density of electrons, mean number of electrons per unit volume, and capital A is the cross-sectional area of the conductor. Okay, now see, if the electrons are drifting through the conductor with a velocity V, as that conductor is lying in a magnetic field, these electrons are moving through a magnetic field. So those electrons will experience a force, and it is given by QV cross B. Here the charge of the particle will be minus E. Okay, so minus EV cross B. This is the force on each electron. And here we are considering a small element of length dl and cross-sectional area A. So the volume of the element will be A dl. Okay, number of electrons in unit volume will be small n. So the total number of electrons in that element will be number of electrons in unit volume into volume of the element, that is A dl. Okay, so Na dl, total number of electrons, into this quantity inside the square bracket is the force on each electron. Okay, so this is the total force on all the electrons in that element, or the magnetic force on that element. Okay, and df we can write NaDl minus EV cross B. I have rearranged certain factors like this. I have minus NaEV and dl cross B outside. Okay, the quantity inside the bracket is nothing but the current. So I can write df equal to I dl cross B. Okay, I dl cross B. This is the force on each element of length dl. Now let us consider a straight long conductor kept in a transverse magnetic fields. Okay, so here is the conductor. It carries a current capital I and it is kept in a magnetic field which is directed along the invert normal. Okay, now see, the direction of the magnetic field is represented by considering the movement of an arrow. Consider a three-dimensional arrow. Okay, like this. I have drawn the arrow here. Suppose the arrow is coming out of this plane. So only the tip of the arrow will be visible. That will be a point. So if the magnetic field is represented by dots, then it represents a magnetic field that is directed outwards or along the outward normal. If the arrow is going into the plane, see, only the back side of the arrow will be visible, means this part that will appear as a cross. Okay, so if the magnetic field is represented by crosses, then it represents magnetic field along the invert normal to the plane of the boards. Okay, so here I have a conductor. Then the magnetic force on L length of a straight conductor, F equals I L cross B. Okay, in this case, the current element IL and the magnetic field are perpendicular to each other. So ILB sine 90. So it will be ILB. That is the force on L length of a conductor, straight conductor, which is kept in a transverse magnetic field of uniform intensity, capital B. Now children, let us find the direction of this force. See, in electromagnetics there are two actions, generator action and motor action. See, there are only three electric machines. Okay, if you take any electric machine, that will be or that will belong to one of these three. Okay, see, what are those three electric machines? Generator, motor and transformer. If you take any electric machine, it will be a generator, or it will be a motor, or it will be a transformer. Okay, no other electric machine. Okay, now see, and this transformer is the most efficient electric machine because it has no moving parts. So there will not be any wear and tear due to friction. Okay, so it is the most efficient electric machine. Children, let us consider generator and motor. Basic construction of generator and motor are exactly same. We will have a magnetic field or two magnetic poles. Okay, there will be magnetic field in between the poles. We will keep a conductor between the poles. It's usually called armature. Leave it. It is simply a conductor. Consider it as a simple conductor. Okay, for the simple construction. So basically both the generator and motor will have a conductor kept in a magnetic fields. Okay, so in both the cases we will have a magnetic fields. So the direction of the magnetic field will be knowing in both the cases, both in case of generator as well as in case of motor. Okay, now children, if you pass an electric current through that conductor, so you have given the electric current also. So in such a case, you will be knowing the direction of the magnetic field and also the direction of the electric current, because current is passed through that conductor. It will experience a force. The direction of that force you will have to find out. And for that, you have to use Fleming's left-hand rule. I have highlighted the letter F in left. That is used to determine the direction of the force. Okay. Now again consider a conductor kept in a magnetic field. Suppose force is given. Means when force is given to a conductor, it will be moving. Means it will be rotating. Okay, so if force is also given, means magnetic field is there, force is given, means the conductor is moved in the magnetic field, then current will be generated. You will have to determine the direction of the current. For that, you will have to use Fleming's right hand rule. Children, please see, I have highlighted the letter I that stands for current. So Fleming's left hand rule is used to determine the direction of force, and right hand rule is used to determine the direction of the current. Now let us find the direction of the force experienced by this straight conductor kept in a uniform transverse magnetic field. Magnetic field is along the invert normal. you have to use the Fleming's left hand rule. Okay, current is, see in this case current is upwards, so the middle finger must be pointing upwards. See in both the left hand rule and right hand rule, forefinger along the direction of magnetic fields. In both the rules, middle finger along the direction of electric currents and thumb in both the rules along the direction of the force. Okay, here current is upwards, magnetic field is into the plane. So children, thumb is directed towards left, so this conductor will experience a force BIL directed towards left. Now let us find the force on two parallel straight conductors. Okay, we have to see long, or let us say infinitely long parallel conductors, okay, carrying current I1 and I2 placed in vacuum. Okay, see I have here a conductor which carries a current I1 and the second conductor carries a current I2. They are parallel and the separation between them is small r. Now see, this second conductor produces a magnetic field at the position of the first conductor. How do you find the direction of that magnetic field? You have to hold the conductor in the right hand with the thumb along the direction of electric currents. So if you hold the conductor, second conductor, okay, then the magnetic field on the left side of the second conductor will be along the outward normal, and it is being represented by a dot. As the first conductor lies in the magnetic field produced by the second conductor, the first conductor will experience a force. And the direction of that force we can find by using the Fleming's left hand rule. Okay, magnetic field is along the outward normal, see. So my forefinger is pointing outwards, current is upwards in the first conductor. So the force on the first conductor will be towards the second conductor. Okay, so first conductor will be attracted by the second conductor. Okay, now see, the second conductor lies in the magnetic field produced by the first conductor. What would be the direction of the field produced by the first conductor at the position of the second? How do we find that? We have to hold the first conductor in the right hand with the thumb pointing along the direction of electric current. Hold the conductor like this. Okay, so the magnetic field on the right side of the first conductor will be along the inward normal, and it is being represented by a cross. So the direction of the force on the second conductor, let us find by using the Fleming's left hand rule. Magnetic field is along the inward normal, current is upwards, so thumb will be directed towards the first conductor. So second conductor experiences a force towards the first, and first conductor experiences a force towards the second. Or if the current in the two parallel conductors are along the same direction, they attract each other. So if they carry current in opposite direction, the magnetic force of interaction will be repulsive. Okay, now see, the magnetic field produced by the second conductor at the position of the first conductor is given by mu 0 I2 divided by 2 pi r. The second conductor is perpendicular to that magnetic field. Then what would be the force on L length of the first conductor? Okay, that is F1 equal to I1 L cross B2. Means it is I1 L B2 sin 90. Okay. Now what would be the force per unit length of the first conductor? It is represented by capital F1 and it is equal to I1B. Okay, because it is to be divided by L. This is the force on L length. So force per unit length will be divided by L. Okay, so that we will get mu 0 I1 I2 divided by 2 pi r. So this this is the force per unit length of the first conductor. See the choice of which one needs to be taken as the first, which one is to be taken as the second. That is purely arbitrary. Any conductor you can take as the first and the other should be taken as the second. As this 1 and 2, that choice is purely arbitrary. What is true for first conductor must be true for the second also. Okay, so if this is the force per unit length of the first conductor, you can easily get the force per unit length on the second conductor by simply interchanging the suffixes 1 and 2. Okay, that will be F2 equal to mu 0 I1 I2 divided by 2 pi r. This is the force on second conductor per unit length and this is the force on first conductor per unit length. Both are of the same magnitude. Okay, and if they carry current in the same direction, it will be attractive. If they carry current in opposite direction, it will be repulsive. So let us say this is the force of interaction between two parallel straight conductors carrying currents I1 and I2. Okay, now children, let us assume that the current in the two conductors are of equal magnitude, or the two conductors carry equal current, each equal to 1 ampere, and the separation between them is 1 meter in vacuum. Okay, so if we put these values, we will get F, force per unit length, as 2 into 10 raised to minus 7 Newton per meter. So if the force per unit length on two parallel conductors carrying equal current kept at separation 1 meter in vacuum is 2 into 10 raised to minus 7 Newton per meter length, then the current in each conductor is 1 ampere. That is the definition of ampere. Now children, see, we have a current loop or a circular loop of radius say small r. Okay, radius small r. Okay, we have a circular loop of radius small r which carries a steady current capital I. Okay, and it is kept in a uniform transverse magnetic field, and that field is along the inward normal to the plane of the board. Okay, what is the resultant force on this loop? Okay, now you may consider a small element, okay, so you can consider this as a straight conductor. Okay, let us find the direction of the force on that element by using the Fleming's left hand rule. Magnetic field is along the inward normal, current is, see, along this direction, so the force will be like this. So this is the direction of the force. Okay, this is the direction on this element. Now consider a diametrically opposite element here. Okay, and the current through that element will be like this. Magnetic field is along the inward normal, current like this, so the force will be like this. Now consider this element. The force is see, along this direction, and the force on diametrically opposite element will be in the opposite direction. So the magnetic force on each element of that loop will be equal and opposite to the force experienced by a diametrically opposite elements. So the resultant force on the circular loop will be 0. But the circular loop will experience a tension. Okay, let us find the tension in the circular loop. Okay, now suppose capital T is the tension, capital T. Okay, so consider, see this element. This is a small element which subtends an angle 2 theta at the center. Okay, so this is the direction along which tension is acting. Same tension will be acting here also. Okay, that tension makes an angle theta with the tangent. Now this T can be resolved T cos theta like this, and see this T also can be resolved T cos theta like this. Okay, and this is the tangential component of this T, and this T will get cancelled. But what about the radial component? See this T cos theta like this and T sin theta to the center. Okay, this T cos theta like this and T sin theta to the center. So T sin theta acting towards the center will get added up. Okay, T cos theta due to in the opposite direction, those T cos theta component will get cancelled. Okay, so the resultant force on that element will be directed towards the center. Okay, now see the current in that element is see this is the direction. This is the direction of the current. Okay, magnetic field along the inward normal, current towards left, so the force will be directed downwards. Okay, and that is equal to 2t sin theta, and it is equal to BIL, where L is the length of the element. Okay, see, length of the element means it is the length of the arc, and it is equal to angle into radius. Okay, BIL, that L equal to angle into radius. So BIL, angle is 2 theta and radius is r. That is BIL. And the resultant force acting towards the center is T sin theta plus T sin theta, that is 2T sin theta. Okay, and when theta is very small, sin theta can be replaced by theta. So on the left side we will get 2T theta, and on the right side we will get BIR in BI into 2R theta. Okay, we have theta on both sides. Okay, we have theta on both sides, that can be cancelled. and 2 on both side, that also can be cancelled, so we will get T, tension in the loop, as BIR. Now children, let's find the ratio of magnetic moment and angular momentum of a charged particle moving in a circular path. Okay, here we have a particle of mass m and charge q moving with a uniform speed v in a circle of radius r. Okay, and see the current is given by charge by periods. Period t we can write 2 pi by omega. 2 pi by omega will go to the numerator, so it will become q omega by 2 pi. Okay, the magnetic moments, see this is equivalent to a current loop, and magnetic moment is current into area. Okay, current we have got q omega by 2 pi, and area will be pi r square. So q omega by 2 pi into pi r square, that is the circular area. So q omega r square by 2, that is the magnetic moment when a particle of charge q is revolving in a circle of radius r with a uniform angular speed omega. Okay, then what is the angular momentum of the particle? Okay, it is moment of inertia into angular velocity. Moment of inertia of a point object is mass into square of its distance from the axis. So it will be mr square omega. See, the ratio of the magnetic moment to the angular momentum is called gyromagnetic ratio. Okay, so magnetic moment mu divided by angular momentum L. This is equal to q divided by 2m. It is a beautiful ratio and it is called gyromagnetic ratio. Okay, now for an electron, see this q by m, actually charge to mass ratio is called a specific charge. Okay, for an electron, this gyromagnetic ratio will be, we know the charge on an electron and its mass also, we can easily calculate, and it is 8.8 into 10 raised to 10 coulomb kilogram raised minus 1. Okay, now see the magnetic moment of an electron. Magnetic moment will be q by 2m into angular momentum. Okay, so q, the charge on an electron is E electronic charge, divided by 2m into angular momentum L. See, in Bohr's theory, angular momentum of an electron is nh by 2 pi, where n is the principal quantum number. Okay, so E by 2m, charge of the electron divided by 2m, and angular momentum is nh by 2 pi. Okay, that is the magnetic moment of an electron. Okay, so the minimum value of n, principal quantum number, is 1. So when you put n equal to 1, you will get the minimum value of the magnetic moment of orbital electron in the hydrogen atom, and it is called a Bohr magneton. Then the Bohr magneton, C equal to EH divided by 4 pi m, where H is Planck's constant, E is the electronic charge, and m is the mass of the electron, that we will get 9.27 into 10 raised to minus 24 ampere meter square. Now children, let us see the current loop in a magnetic field. See, I have a long copper wire. Okay, and see that long copper wire is wound in the form of a rectangular coil. Okay, now suppose this is the rectangular coil. Okay, and each page of this book you can consider as a turn. Okay, now this is kept in a horizontal magnetic field. A magnetic field is like this, horizontal. And see, this rectangular current loop will act as a magnetic dipole, and the dipole moment is along the outward normal. Okay, see, normal to the plane of the coil makes an angle theta with the direction of the magnetic field. Magnetic field is along horizontal, and this is the outward normal. Okay, and see this conductor, this is of length L, and this is the breadth of the rectangular coil. This conductor will experience a force BIL like this, and this conductor will experience a force BIL inwards. Okay, see, when you look from the top, you will see only this part that is being shown here. Okay, this is the top view. Okay, and this conductor experiences a force along inward, that is BIL, and this experiences a force along outwards. Okay, so this BIL and this BIL, the perpendicular distance between them will be, see, this is B and this will be B sine theta. See, it is shown here, BIL like this, BIL like this. See, these two equal and opposite forces will constitute a torque, and the turning effect is either force into perpendicular distance between them. Okay, and see, this is the line along which this force is acting, this is the line along which this force is acting. The perpendicular distance is B sine theta. and the torque is either force BIL into perpendicular distance is B sin theta. So this is ILB into capital B sin theta. Okay, this L into B, that is length into breadth, that is the area of the loop. Okay, and it is I into A B sin theta. I into A, that is the dipole moment of the coil. So we can write MB sin theta. Theta is the angle between the dipole moment and the magnetic field vector. So we can write M cross B. So when a current loop is placed in a magnetic field, it will experience a torque, and that torque is equal to M cross B. Now see moving coil galvanometer. Okay, see in moving coil galvanometer, see a rectangular coil will be kept in a magnetic field. See, if the magnetic field is uniform, and suppose the magnetic field is along the horizontal, and suppose we have kept a rectangular coil like this, then the magnetic flux through this coil is the magnetic flux passing normally through the coil. When the coil is like this, the whole magnetic lines of force will be normal to the coil. See, but when the coil is turned like this, the magnetic lines of force or magnetic flux through the coil will be B cos theta. Okay, so as the coil rotates, the magnetic flux through the coil will vary as cos theta. So when theta equal to 0, the flux through the coil will be maximum. When theta equal to 90, the flux through the coil will be 0. Okay, so the torque experienced by the coil will be proportional to cos theta. So we won't get a uniform scale. See, I have changed the magnetic field like this. See, in this case, if the coil is like this or like this, whatever be the orientation of the coil, see, if the coil is like this or like this or like this, whatever be the orientation, the magnetic field intensity through the coil will be the same. So everywhere or at any position of the coil, we will have the same magnetic field intensity B. Okay, so the current to be measured will be passing through the coil, and the coil will experience a torque NIAB. See, as this coil is being suspended by a metal strip, not string, it will not be cylindrical. It will not be a cylindrical wire, instead it will be a strip. Okay, so this coil is suspended by means of a strip. Okay, the current to be measured enters the coil through this phosphor bronze strip. Okay, it passes through the coil, through all the turns of the coil, and leaves the coil through a copper spring. Okay, so this coil will experience a torque and it turns, then this phosphor bronze strip will get twisted. Okay, as it gets twisted, a restoring torque will be developed in it, and it is given by C theta. When this driving torque equals restoring torque, it reaches equilibrium. Okay, and this constant C is called a torsional constant. So the current to be measured, I, equal to C divided by NAB into theta, and we can write C equal to G theta, where G is the quantity inside the bracket, and it is called galvanometer constant. Okay, now the deflection for unit current is called current sensitivity. Okay, so S sensitivity with the suffix I means current sensitivity, that is equal to theta by I. That is equal to NAB by C, where C is the torsional constant. If capital R is the resistance of the coil, then voltage sensitivity, that is equal to the deflection per unit voltage theta by V, that is equal to theta by IR. Means in the denominator we have to put R. Okay, so NAB divided by CR, that is the voltage sensitivity of a galvanometer. Next is conversion of galvanometer into an ammeter. See, galvanometer is an instrument used to detect the current rather than measure the current. Okay, means it produces a large deflection even for a small current. Okay, see, we have a galvanometer and its resistance is capital G, and it is capable of measuring a maximum current of Ig. Ig is the I with the suffix G is the full scale deflection current. Now suppose you want to convert it into an ammeter capable of measuring a maximum current capital I. Okay, this is, see, you have now the galvanometer is capable of measuring a maximum current Ig. You have to convert it into an ammeter to measure a maximum current capital I. Then I by Ig, that is N. Okay, you have to connect a small resistance in parallel with the galvanometer. That small resistance is called shunt, and it is equal to G by N minus 1. Okay, now see children, how do we convert it into a voltmeter? Okay, see we have a galvanometer. See, it is capable of measuring a maximum voltage Vg. That Vg is actually equal to galvanometer resistance into full scale deflection current. It is to be converted into a voltmeter capable of measuring V. Okay, then V by Vg is N. Means actually its range is to be improved by a factor N. Okay, and see in case of this ammeter, see its current range is to be improved by a factor N. Okay, voltmeter case also, see voltage is to be improved by a factor N. Then a high resistance is to be connected in series to convert it into a voltmeter. That high resistance is N minus 1 into G. Okay, to convert it into an ammeter, a small resistance is to be connected in parallel. It is G by N minus 1. So first thing you have to do is you have to find that factor N. Okay, means it is the maximum range into which it is to be converted I divided by Ig. Okay, and in case of voltmeter it is V by Vg. This high resistance that is to be connected in series with a galvanometer, it's called a multiplier. See, what is the resistance of an ideal ammeter? It is 0. We cannot have a practical ammeter with a 0 resistance. So its resistance must be as small as possible. See, to reduce the resistance, we should connect a resistance in parallel. So the effective resistance will be smaller than the smallest. So if you connect a small resistance in parallel, effective resistance will be even smaller than that. So G by N minus 1 is to be connected in parallel. An ideal voltmeter must have infinite resistance. You cannot have a practical voltmeter with the infinite resistance. So the resistance must be as high as possible. In order to increase the resistance, a resistance must be connected in series. So if you connect a high resistance series, the effective resistance will be even more than that. Okay, right. Now what we have next, see this is, we have two parallel stream of particles. Okay, the particles of charge Q1 are moving with velocities V1 and particles of Q2 are moving with velocity V2. Okay, the perpendicular distance between these two streams, let it be R. Okay, now see this is equivalent to a current. Okay, if both the particles are of positively charged, then these two are equivalent to current in the same direction. So the magnetic force will be attractive. But as these charged particles are of similar nature, electric force will be repulsive. So there will be magnetic attraction and electric repulsion. What would be the nature of the resultant force? It will be attractive or repulsive. That will depend on the relative magnitudes of electric force and magnetic force. Okay, now see B1 that is the magnetic field due to the first stream of particles at the position of the second stream. Okay, that is by Biot-Savart's law, because this is equivalent to a current carrying conductor. Consider a small element of length dl, mu 0 by 4 pi I1 dl sin theta by r square, theta is 90. So I1 dl divided by r square, that dl I can write velocity into a small interval of time delta t. Okay, so we will get B1 equal to mu 0 by 4 pi I1, dl is V1 delta t by r square. Okay, and see this I1 delta t, current is charged by time. So current into time will be charged. So I1 delta t I can replace by Q1. So this is the expression for the magnetic field at the position of the second stream of particles due to the first stream of particles. Mu 0 by 4 pi, Q1 V1 by r square. Okay, now the second stream of particles are moving through the magnetic field produced by the first stream of particles. So each particle of the second stream will experience a force that is given by F2 equal to Q2 V2 cross B1. So F2 equal to Q2 V2, this V2 and B1 are perpendicular. So V2 B1 sine 90. So I have written B1 here. Okay, so this is the magnetic force between the experienced by the second stream of particles. Okay, how do you get the magnetic force experienced by the first stream of particles? You have to simply replace the suffixes 1 and 2 or interchange the suffixes 1 and 2. Okay, so let us say the magnetic interaction between the two parallel stream of particles Fm, that is equal to mu 0 by 4 pi q1 v1 q2 v2 by r square, and the electric force of interaction Fe, that is equal to 1 by 4 pi epsilon 0 q1 q2 by r square. Okay, and see, now let us find the ratio of the magnetic force to electric force. That we will get v1 v2 by v1 v2 into epsilon 0 mu 0. Children, 1 by root of epsilon 0 mu 0 is c, the speed of electromagnetic waves or light in vacuum. Okay, so this epsilon 0 mu 0 can be replaced by 1 by c square. Okay, so we will get v1 v2 by c square, and we can write it as v1 by c into v2 by c. v1 and v2 are the velocities of the charged particles, means material particles, and those velocities will be definitely less than the velocity of light in vacuum. So the first factor v1 by c must be less than 1. Second factor v2 by c also must be less than 1. So the product will be less than 1, or we can say Fm less than Fe. So electric force is stronger than the magnetic force. Here the electric force is repulsion and magnetic force is attraction. So the resultant force will be repulsive. Children, I have explained everything from this chapter. Okay, so I hope that you have noted down, see all those things that you don't know or that you feel it is important. Now, let me tell you again, you have to solve and practice the questions by keeping this notebook open. Okay, please do not try to memorize anything. Okay, see, if you solve the questions continuously, you will remember all formulae and equations that is required to solve the questions. Okay, thank you for watching and all the best.